Hi Physics 100, this is Dr. Ricardo. This is the third video for the electricity chapter. This video is going to focus just on doing the calculations for electric circuits. So the first thing that I have up is a summary table that I put together that you should use as a reference when you answer the questions related to electric circuits. So the first thing is, how do you calculate the resistance of multiple resistors whenever they are in series versus parallel? And then the second thing is, what similarities do you have when you have a set of resistors that are in series in terms of the voltage and the current? What can you say about them? And the same thing for a system where two resistors are in parallel. So if they're in parallel, what can you say about the voltages and what can you say about the currents? So the first thing is, what's the formulas? So whenever you have a set of resistors that are in series and you want to find out the total resistance, all you do is add up the sum of the individual resistors. So if there were three in a row, you add up the first one plus the second one plus the third one. So for instance, if this resistor right here had a resistance of 10 ohms and this one had a resistance of 5 ohms, I would just add 10 plus 5 is equal to 15. If there was a third one down the line that was another 10, I would add 10 plus 5 plus 10 to give me 25, right? 10 plus 5 plus 10. Okay, so that's very easy. When they're in parallel, the formula is a little bit more complicated because what happens is that you create a second pathway. So the total resistance for both of them isn't going to be, oh, I have to go through this hardship and then this hardship, because all the current is going through both of these. Here, the current gets to split up. Some gets to go this way and some gets to go this way. So it's not like, oh, I had to endure the first one, then I had to endure the second one. Because if you get to endure the first one, you don't have to go the second way. You only go one way. So what's going to happen is when you have two resistors in parallel, the total is going to be less than any of the individual ones, okay? In a very simple case where if they both have equal resistances, let's say this one is 10 and this one is 10, then the total resistance turns out to be 5, and we're going to do the calculation in a second because, hey, I have another pathway. I don't have to go this way. If that's too hard, I can go the other way. So the overall resistance is actually going to become 5. It's going to be half as much as either pathway. But let's do the calculation to be sure. Okay, so the way you do the calculation when they're in parallel is if this one was 10 ohms and this one was 10 ohms, okay, I would say 1 over RT is equal to 1 over 10 plus 1 over 10. Okay, so 1 over 10 plus 1 over 10 means 0.1 plus 0.1, right? So I have 0.1 plus 0.1 is equal to 0.2, but I'm not done. That's 1 over RT, where RT is the total. So what is RT? RT, if 1 over RT is 0.1, then RT is 5, because I need to take the reciprocal of that. So 1 over RT is equal to 0.2, so RT is equal to 1 over 0.2, right? And what is 1 divided by 0.2, or 1 divided by 1 over 5? 5. You can do it on your calculator if you want. So this guy's going to have 5 ohms. So that's going to happen when both of them have the same, resistance. The overall resistance is going to be halfway between them, okay? Or not better way to say halfway between it, it's going to be half of either value, okay? What happens if they have very different numbers? Like let's say one is 1 and the other one is 10. Well, most of the current is going to want to go through the one that's 1, right? So what's the 10 going to do to it is just going to bring it down, but I guarantee you the answer is going to be a little bit less than 1. But let's try that, okay? So one of them is 1 and the other one is 10. What's the total resistance? So just do the formula. 1 over RT is equal to 1 over 1 plus 1 over 10. Right? That's what the formula says. 1 over R total is equal to the sum of 1 over the first one plus 1 over the second one. There is no third one, so you don't add a third one. If there would have been 3 in parallel, another one down here, another set of squiggly lines, then I would just have 1 over 1 plus 1 over 10 plus 1 over whatever that third one is. But I don't. I have just 2. So what's 1 over RT? 1 over RT. 1 over 1 is still 1, and I have 1 plus 1/10. So this is 1.1. So RT, I just have to take the reciprocal of that number. 1 over RT is 1.1, so RT is 1 over 1.1. It's going to be like 9 point something, but let's see. 1 divided by, so you just hit 1 divided by 1.1. 0.909, so 0.91 ohms. Okay? So that's what's going to happen, is if one of them is very different than the other, it's going to be very close to the lower one and a little bit less than the lower one. Okay? But just use the formula like that. Okay? There is one more trick that you could do. I'll show you on the back of the sheet if you like that better. If there's only 2 resistors, you can do a little bit algebra to talk about, take the original formula, rearrange it. I'll just leave it here if you want to try it yourself, okay? And you can get that RT is equal to the product of the 2 divided by the sum of the 2. So some people might like that. So let's take our case with one of them is equal to 1 and the other one is equal to 10. Maybe that's a little bit faster for you. So R1 is equal to 1 and R2 is equal to 10. Let's try this formula where it's the sum, the product over the sum. So what do I get? 10 times 1 in the numerator and 10 plus 1 in the denominator. So I get 10 elevenths, okay? And 10 elevenths is going to be 0.91, but we'll just make sure, right? 10 divided by 11 gives you that same number. So that's your choice. If you just have 2, now you can't do that if you have 3, but if you just have 2, you can take the product over the sum. So sometimes I'll do it one way, sometimes I'll do it the other way. You get to choose. Okay. You don't need that yet? Let's go back to this. Okay, now let's do some other things that are logical. So now we know how to do the calculation, but when I have resistors that are in series, what happens to the voltages? Well, the voltage drops, okay? How much? Now you're coming out of the battery over here and you're going to go back around and head back to the battery over here. The voltage drop across each of these resistors in series are going to be additive. So you're going to drop a certain amount across this one, then you're going to drop a certain amount across this one, and at the end of all of the ones in series, they better add up to the voltage of the power supply or the battery. So let's say the battery is 9 volts, then maybe you drop 5 over here and 4 over here. So it's kind of like pushing the electrons around in a circle and go back to the battery. The voltages are all going to be additive. In what situation? When they're in series. Okay. The current is very easy. The current is the same throughout all of them when they're in series because all of the electrons have to go the same path. They can't split up. There's no splitting up in series. Every electron has to go through this same path. Every electron has to go through number 1 and number 2. So again, when they're in series, the voltage adds up and the currents are all the same. When they're in parallel, the voltages are all the same and the currents get split up or the currents add up. So if I had 2 amps of current and these were both equal resistances, one of them would go this way, one of them would go this way, and they would add back up to 2 over here. So it would be 2 amps going in, 1 amp, and then 2 amps coming out. That makes sense because you're watching, current is like watching the water flow. If one was an easier pathway than the other, let's say this one was twice as easy, then twice as much would go through here, then would go through here. So if I had a total of 3 amps coming in and this one was twice as easy, 2 would go this way and 1 would go that way. Okay, and then they would get back together and the 2 plus 1 would go back to be equal to 3. So what happens to the currents when you have resistors in parallel? the currents get split up between the resistors, or another way to look at it is you add the currents back up to get the total current that was coming in or going out. Okay, and the voltages are the same because remember, voltages are the drops across. So if you are coming downhill and you choose to go across this hiking path, or you choose to go across this way, if you meet up in the same place as your friend, you must have had, even if you had a totally different experience, a totally different path, you can't meet up unless you're meeting up at the same height, right? You got to get to the same place. So it's kind of like a state function. This guy and this guy, the voltage drop across this one and this one have to be the same. So look at this. In parallel, this guy and this guy are the same. Parallel, this is the same. Current, this is the same. These add up and these add up. But again, this is going to be open book, so you can pick which one you want to use. Okay, so this is your cheat sheet. Okay, so that being said, let's pick a question that I made up. Great example of a test question. And for the rest of this video, let's go through what it says. Okay, so first thing, and I'm going to walk you through all of the calculations. First thing is, for this DC circuit, now how do I know it's DC? Because I see that this is a battery over here. Okay, so for this DC circuit, I have a 100-volt battery, and then it goes off, and I have two resistors here that are in parallel to one another, right? Then goes around to this resistor that's in series with those two, comes around, splits up to these two resistors that are in parallel with each other, and then they all get back together before they go into the end. Okay? All right. So first question, what is the current flowing through the whole circuit? Okay, so to answer question number one, the only way to answer question number one is you need to calculate what is the overall resistance. Okay? What is the R total for the whole circuit? And the way you do that is you first take all the little sections that are in parallel, like this one, and come up with what their equivalent resistance is. In other words, replace those two resistors by one that would be in between, one that would take their place. This is going to be the one that's going to take those two places, and it is going to go right in between here. And instead of having those two, this guy's the replacement. If I could do that over here, replace these two with one that's in series, and replace these two with an equivalent one over here, and I'll draw that one right here. So replace these two with this one, replace these two with this one. So I'll do that, and I want to replace these two with that. Okay? All right. So how are we going to find out this first resistance? Okay. Well, I'll tell it to you by hand, and then we'll do the math anyway. Okay. What did we say? When two resistors both have the same resistance, and they're in parallel with each other, the equivalent resistance is half that amount. Because here comes the current. It's got an easier path. You made, by adding the second one, see if I only have one, they all have to go through that way. So that's 10 ohms, that stinks. Well, if I add another lane, and it has the same difficulty as the first one, well, half can go this way and half can go that way. That's twice as easy as it used to be, because now I have another lane on the highway. So I'm going to tell you, this guy is going to have an equivalent that's 5 ohms. But let's do it anyway. 1 over RT is equal to 1 over 10 plus 1 over 10, right? 1/10 plus 1/10 is 2/10. 2/10 is 0.2. So then RT, we said, have to flip it over, is 1 over 0.2, and 1 over 0.2 is 5. So we got that one. Okay? So this, an equivalent, if I erase those two and just put one in between, is 5. So when I'm coming around, it's like I had a 5 over here and a 15 over here. So when I get to here, 5 plus 15 is 20. Why? Because when they're in series, I just add them up. Okay, now I have to replace these two with an equivalent. Now I can't just, I know the answer is going to be a little bit less than 5 because this is the easier pathway. Twice as much water or twice as many electrons is going to go this way as compared to this way. Why? It's twice as easy. 5 versus 10, right? So until this guy gets filled up, nobody's going the other way. People only go the other way when they don't have a choice, right? You always take the Garden State Parkway to the beach unless you get so much traffic, then you get up and go through the side roads. And so sometimes you still regret it. Okay, so this is like the side roads. Okay, so how am I going to do that calculation? I'll do that right here. Okay, let's see what it's going to come out. I'm telling you, it's going to always be less than the lower of the two, because by adding this second pathway, right? If there was only one pathway, it would be 5. By adding the second pathway, you have to help, right? By creating a back road, it's got to make it less. Some people are going to take the back road, right? Most people stay on the Garden State, but some people take the back road. So it's got to be less than 5, but let's see what it is. So 1 over RT for that situation, just these two guys down here, is equal to 1 over 5 plus 1 over 10. Okay? What's 1 over 5? 0.2. What's 1 over 10? 0.1. 0.2 plus 0.1, 1 over RT is equal to 0.3. So RT is equal to 1 over 0.3. You just have to flip it over. Okay, let's get that. 1 over 0.3, 1 divided by 0.3. I've got a feeling it's going to be 3.33, and it is. So RT is 3.3. So what did I tell you? It's always less than the lower one. In this case, it's significantly less. Okay? All right, so going through this way where I have a choice would be equivalent to be going through one that was 3.3 ohms. Okay, now I have it easy. I have a 5 here, a 15 here, and a 3.3 here. So what will I have to do? Add them up. RT for the 3 that are in series are 5 plus 15. Just go around in a circle, get all of the resistances, plus 3.3. So this is 23.3. The total resistance all the way around now, I could take all of that stuff and replace it by one resistor. That's 23.3. Now, if I know the total resistance and I know the voltage total, right? That's what's coming from the battery. The battery gives you the total voltage. It provides the push. This is the negative side. The shorter side is negative. The longer side is positive. So we're pushing electrons because electrons are negative around this way. Okay? So that being said, if the total voltage is 100 volts and the total resistance is 23.3 ohms, how do I get the total current? Going around and coming through the battery. It's only going to break up here, then be going through here, then break up here, and then come around here. So I total will always be what's going through any place where all the electrons are together, like right going into the battery, coming out of the battery. Here it'll be total, here it'll be total, here it'll be total. Here it's going to break up, then it's going to be total. It's going to be total a lot of places. Any place where there's only one pipe. It doesn't have any choices. Okay, so how are you going to get I total? Well, you're going to get I total by V is equal to IR, our most important formula. So V is equal to IR, and you have V and R, what's I? I is equal to V over R. So I total is equal to V total over R total. All right, so 100 volts divided by 23.3 ohms. Answer to the first question, going to be a little bit more than 4. So 100 divided by 23.3. 4.29. Okay? 4.29 amps. Okay, so what's going through the battery right here, what's coming out, is 4.29 amps. What's coming back into the battery is 4.29 amps. What goes in has to come back out, right? That goes out. Let me move this around. How's that? That goes out, got to come back in. You got to make a circle. Everything that goes out, you don't lose any electrons, has to come back in. Okay, so what is the current flowing through the whole circuit? 4.29 amps. And A is amps. Okay? If I were to ask you question 0, what is the overall resistance of the whole thing? That was 23.3. So I'll ask them in a selective way. I'll ask them in order, so it's easy to realize what you're supposed to do next. So we can call that question 0. All right, now we're going to make a little table. What is the voltage drop across each resistor? Okay, now over the process, here comes my little table, okay? All right, so each resistor, I have R1, let me see what makes sense to do it this way. It's not good. What is the voltage drop across each resistor? So what I could do here is, here's R1, here's R2, here's R3, here's R4, here's R5. So we want to know the voltage across that resistor. What's the voltage going across it? And what's the current going through it? Okay. All right, so R1. All right, here I go. I come into here. I originally have 100 volts to play with. When I have to go through either this path or this path, there's going to be a loss. I'm going to lose some voltage. It's going to go down. Then I'm going to come down. I'm going to lose some more. Then I'm going to come this way. Maybe I'm going to go this way. I'm going to lose some more. I'll tell you one thing. By the time I get finished with any pathway, maybe I go this way, then this way, then this way, I have to lose 100 because I got 100 to lose. 100's going in. Maybe another electron goes this way, and this way. Well, guess what? Any pathway that you take, you're going to have to lose 100. So that's our check at the end. Any pathway, you're going to lose 100. You don't ever go through this one and this one. You go through this one or this one. So that's not a pathway, right? You just pick all the different versions and they'll add up to 100. Okay, so how do you figure out what the voltage is across them? Well, we know the current coming into here, right? The current coming into here. Let's do this one first, okay? So if 4.29 amps is coming through here, let's hold off on doing these two. When they get back together, all of the current that went in here splits. Half of it goes this way and half of it goes that way, right? So that's actually pretty easy. Why do we know that? Because there's the same resistance. So if half goes this way and half goes this way, to get the current, we just have to cut this number in half. So 4.29 divided by 2 gives us 2.14, 2.14. So how much is the current going here? 2.14 amps goes this way, right? And 2.14 amps of current goes that way. And then here comes 2.14, 2.14. They get back together to make, what's going through here? 4.29. So we can actually go in, and for R1 and R2, what's the current going through them? This one is going to be half, 2.14. This one's going to be half, 2.14. Okay. How are we going to get these two voltages? Does that make sense? Why are they half? Because half of it went this way, half of it went that way, because they had the same exact resistance. One wasn't harder than the other. So half the cars go this way, half the cars go that way, half the water goes this way, half the water goes that way, half the electrons go this way, half the electrons go that way. 4.3 divided by 2, 2.15. Makes sense? Then they add back up to this here. Okay. How much current has to go through R3? Everything. It's the only pathway. So we can get this one, right? That's got to be back to 4.29. Add them back up, right? Coming through here. Now, these two numbers aren't going to be the same, right? They're not going to be the same like they were up here. Why? Because this is an easier pathway, this is an easier pathway than this one. So twice as much is going to go through here as is going to go through here, okay? And then they're going to add back up. So you go by how hard the pathway is, okay? But let's hold off on that for a second. But I know one thing, those two are going to add back up to our 4.29. All right, let's do a couple of voltages and then we'll come back and fill in this table. The way you get the voltage drop is V is equal to IR. You know the resistance here is 10. you know the current going through had to be half of the total, which is 2.14. So all I need is 10 times 2.14. So 10 times 2.14, right? 2.14 times the resistance is 10. Look, I'm doing R1 now, right? This guy's got a 1 over here. This guy's got a 10 times 2.14. The voltage is equal to the resistance times the current through that particular resistor. Sorry, I lost my screen. So 10 times 2.14 times 10 gives me 21.4. So the voltage drop across this one is 21.4. The voltage drop across the bottom one is the same. Look, it has the same exact current and the same exact voltage. It's in exactly the same situation. These two guys are twins. Twins in parallel have everything the same. So this guy also has a drop of 21.4. So I had 100. I now dropped 21.4, right? I'm down to 79-ish, right? 9.6. All right, don't worry about that yet because we're going to calculate this guy next, okay? Now, same thing. V is equal to IR, right? If I want to know the voltage situation for this resistor, the voltage drop, it's coming in. It's got a lot of voltage. Oh, I got to make my way through this terrible, terrible resistor. By the time I come out the other side, my voltage drop is going to be V times IR. So put in the resistance and the current at that resistor. You know 4.29 is coming in, and you know 15 is there. So it's just 4.29 is the current, 15 is the resistance. So I'll do that over here. 15 is the resistance. The current was 4.29. This is for V2. Excuse me, R3. Okay, so for R3, the voltage at R3 is V3 is 15 times 4.29. So 4.29 times 15. 64.35. So how much is going to get lost over here? I'm going to round it, 0.35. Let's make it 64 point, I have 60.35, 64.4. All right, now watch this. I got two more, okay? Now, either one of these pathways, I could almost get this one by difference. Either one of these has got to get me back to 100. There's only one more way. I got to go this way or this way. So if I take how much I dropped after the top ones, right? 21.4, right? I had to go through either one of these two. Then after I went through one of those, everybody's got to go through this. So this one plus this one has got to be how much I drop either here or here. Remember, look at the cheat sheet. The voltage drop is going to be the same across resistors, right? Voltages are going to be the same across resistors that are in parallel. They're going to have the same voltage drop, okay? But we can calculate either one, okay? So first thing I'm going to do is let me partition this current, right? So we know that 4.29 is coming in. Amps, right? This way is twice as hard as this way. You agree? They're not equal. Twice as hard as this way. So 2/3 of out of the total of 15, 2/3 of the current are going to go this way, and 1/3 of the current is going to go this way. Now that's one way of looking at it. You get the current first. If not, you can figure out what each one of these resistors are, so I'll do that way too. But right now, follow my logic, right? 10 plus 5 is 15. 2/3 goes this way, and 1/3 goes this way. Why 2/3? This is twice as easy as this. Okay? All right, so if 2/3 go this way, I need 2/3 of 4.29. So 4.29 times 0.666. Okay, so the current going through R4, which is the top one, is 2.8 2.86. So this one is 2.86. So more is going through there. 2/3 of it goes through there. And 1/3 of it goes the other way. So here comes all of it. This way is harder, twice as hard. So a lot less is going to go through. Most of it's going to go through that way. So let's take 1/3 0.333 times 4.29. Okay, so this way 1.43 goes that way. Okay, so my partitioning is 2/3 go the easy way, 1/3 goes the hard way. All right, because this is twice as easy as that. Okay, all right. Now, if that's the case, how do I get my voltage drop across them? Now, I better get the same number, right? We said the voltage drop will always be the same. Okay, well, this one, if I want to get R4, I need to take 2.86 times 5. Take the voltage and the current at any spot. Here's the current, here's the voltage. I get 14.3 over here. Better get 14.3 over here. Right? My current is 1.43. My resistance is 10. Voltage is always equal to, I'm doing voltage right now. Voltage is I times R. I times R. Okay. All right, well, that's easy. 10 times 1.43 is 14.3. All right, so I got my whole table. Let's see if it makes sense. Okay, first thing, any pathway that I go around, well, first of all, the currents always have to divide up and add back up to the total current, which is 4.29. So here comes 4.29. Half goes this way, 2.14, 2.14, gets back together to make the whole 4.29. Everybody goes through here. All the current goes through here. Comes down to here. How much current goes this way? 2.86 ohms, amps go the easy way. And 1.43 go the hard way. Okay? The 2.86 plus 1.43 better add up to 4.29. Let me check. 2.86 plus 1.43, add back up to 4.29. Here comes my 4.29, back around the other way. The whole thing gets boosted by the battery, and out comes my 4.29, breaks up, half and half, back to the hole, comes around, 2/3 this way, 1/3 that way, back to the hole, woof, keep on going around. See, everybody split, all the electrons, everybody's through here, all the electrons, split, most of them go to the top because it's easy, come back around, boom, okay. So that's the first thing, all the currents have to, whenever the pipes get back together or the wires get back together, they have to add back up to the hole, so we got that right. Next, the voltage drop all the way around, whichever pathway I go to, has to give me 100. So let's go all the way around the top. How much drop did I get if I go through 1, then 3, then 4, right? That's one pathway. One electron might take this, right? Go all the way the tops. So if I do all the way the tops, I got 1, 3, and 4. Okay, we better add 1, 3, and 4 up. 21.4 plus 64.4 plus 14.3. Bam. 100.1. So if I go all the way around the top, what's my voltage drop across here? I have 100. How much do I drop when I go across the first one? I go down 21.4 volts if I go this way. All right. Number 3, I had that one. I go down 64.4 volts. I drop here. I'll circle those. If I go this way, how much do I drop across number 4? 14.3. Okay, so I'm circling all the voltage. So path 1, that guy. That guy, and that guy add up to 100. Okay, let's go all the way around the bottom. Take this road. Everybody's got to go through there. Take that road. Okay, this one has the same exact numbers as this one, right? Remember, they were twins. They had the same current, the same voltage, and the same resistance. Look, same resistance, same current. So this is also, I got to drop 21.4. So here I come. I got 100. I dropped 21.4. Then I dropped 64.4. Then I dropped down here. What's R5? R5 was also 14.3. This top one was 14.3. This bottom one was 14.3. The only thing different about them was the currents. So if I go the total bottom route, 21.4, 64.4, and 14.3, also add up to 100. This way, and this way. See, if I go that way, any pathway, I've got to use up 100. Okay, last one. How about if I go the top here, but go the top, I did top, let me go top, bottom. See what other pathway I could go. So I did go the tops, go the bottoms. Let me go the top here, and the bottom here. 21.4, 64.3, 14.3 adds up to 100. Go this way. 21.4, 64.3, 14.3. Any pathway, if you follow it and do the circles, you got to get to 100. Okay? So, this is the answer to everything that you could possibly be asked for. See if they make sense to you. These voltages, these are in amps. These are in volts. We'll do one of these during a problem-solving session. But this is a very good example of one of the kinds of questions I'm going to ask you on the third test. Okay? A lot of logic. And it all comes back down to this is going to be your cheat sheet, right? The voltages drop when they are in series. The currents are the same. When they're in parallel, the voltages are the same, and the currents add up. So these two add, these two are the same. Okay, see you next time.